Welcome to the talk on the CH2 benchmark, showcasing Couchbase Server 7.0. My name is Vijay Sarathi, and this is joint work with Michael Carey, Dmitry Lychigin, Murali Krishna, and Till Westman from the Analytic Service engineering team. In this talk, we will talk about traditional OLTP and OLAP processing, introduce the concept of HTAP/HOAP, provide a brief background of standardized benchmarks, and then talk in depth about the new CH2 benchmark and how it showcases Couchbase's architecture. Historically, operational or OLTP and analytical or OLAP processing were separate activities, each running on their own separate infrastructures. Periodic ETL processes would extract and load the data from the operational side to the analytical servers for analyzing the data. However, this had the limitation of not being able to provide real-time analytics. To address this limitation, architectures with hybrid data management support called HTAP or HOAP are becoming the norm in the relational SQL world to provide real-time data analytics in today's world of mobile and web applications. With the advent of the emerging NoSQL world, the need for HOAP and real-time analytics are equally important. The natural question to ask then is, how do you measure the hybrid operational and analytical processing capabilities of a NoSQL database? In other words, the HOAP capabilities or the hopefulness of a NoSQL database. To answer the question about how to measure the hopefulness of a database, it is important to measure mixed workload performance, but unfortunately, typical standardized benchmarks measure either transactional or analytical workload performance, but not both. Well-known benchmarks in the relational world are TPC-C for transactional processing performance and TPC-H for analytical query performance. Here's a quick recap of the familiar TPC-C and TPC-H schemas for reference. As we can see, while the two schemas are different, there are also many similarities. Both the schemas have order, order line, and customers. Given the similarities and the fact that TPC-C is used for measuring transaction processing performance, while TPC-H is used for measuring analytical query performance, a natural question to ask then is, can these benchmarks be somehow merged to design a mixed workload benchmark? Designing a brand new benchmark is non-trivial. So we started looking for any previous work on mixed workload benchmarks and came across the CH benchmark, which is a hybrid benchmark. It was introduced by a group of database query processing and performance experts at the DB test workshop in 2011. The CH benchmark executes a complex mixed workload by combining an OLTP workload based on TPC-C and a corresponding OLAP TPC-H equivalent workload, thereby providing a foundation for mixed workload performance evaluation. Since it is based on well-established benchmarks in the relational world, we thought it would be perfect to use CH as a starting point to design a viable benchmark for the NoSQL world. We introduced the CH2 schema as a modified version of the CH schema adapted for the NoSQL world. The CH and the CH2 schemas retain all the tables from TPC-C. From TPC-H, the part subtable is removed. The part table is replaced by the item table. In the original CH schema, line item table is replaced by the order line table. Supplier, nation, and region are borrowed from TPC-H with a few modifications. In the CH2 schema, we denormalize and combine the orders and order line tables into one by having order lines inlined as arrays inside of the orders collection. As shown in the figure, some collections are used for OLTP only, some for OLAP only, and some for OLTP and OLAP, both. This slide illustrates how order lines are stored as arrays inside an orders object. This is a document within the orders collection, has an OID of 1, and order lines are embedded as array elements inside the O order line array. In a flat relational world, each of these would have to be replicated for the same OID. The CH2 workload consists of the TPC-C transactions and the OLAP queries workload. The TPC-C transactions are exactly the same as the original TPC-C transactions: new order, payment, order status, delivery, and stock level. The OLAP queries are modified versions of the original 22 CH queries, which were themselves based on the 22 TPC-H queries. Example OLTP transaction, the new order transaction. Notice the highlighted portion at the bottom of the slide that shows the query being adapted for the nested version of orders. You see the reference to O order line here? That's a nested array here. No need to look at the other details here, but the takeaway is that these are very simple point queries based on keys and run very fast with the appropriate indexes. In contrast, the example OLAP query, query 8 of CH, is very complex with multiple joins, grouping, and order by, and needs a lot of engine processing power to execute. This is from the original CH benchmark specification. Notice the highlighted parts of the query, which we will change with CH2. Now, while executing this mixed workload, most systems will suffer transaction throughput degradations due to the analytics queries and vice versa. The CH2 benchmark therefore provides a mechanism to measure the performance of hybrid systems running a mixed workload. During our initial analysis and run of the original CH queries, we discovered many significant issues. The CH folks had written a data generator based on TPC-C. So the main problem was TPC-C's so-called Big Bang. All of the date fields in the initial CH database had the current date. As a consequence, there were no date ranges to be found in the data. This was a huge problem because TPC-H queries are designed to operate on a 7-year history. So as a result, the CH queries, which were supposed to be TPC-H-like, were not meaningful. The CH query predicates in some cases return the whole table, or in other cases return no rows, or did not conform to the TPC-H specified selectivities. To summarize, the CH queries in their original form were not in sync when combined with the initial CH data, and so a redesign was needed. So we carefully addressed all the issues that we talked about and designed a CH2 benchmark. To address the date issues, we introduced a run date that controls the historical characteristics of the data. We designed start date to be run date and run date minus 7 years, and end date to be run date minus 1 day, to generate a date range of 7 years like TPC-H. Then we fixed the dates in orders, the fields O entry D and OL delivery D, similar to TPC-H. We generated a denormalized orders collection. Then we fixed the date ranges and predicate ranges in the analytical workload queries to conform to the TPC-H predicates and the TPC-H query business semantics. We used DSQGen to generate query templates for all the 22 queries so that randomized constants can be generated to run the benchmark. As an example of the changes, the left side on this slide shows the original CH query 3, and the right side shows the modified version of query 3. In the original query, the predicate in red returns the whole table. In the modified query, note the denormalized orders reference in the from clause and the randomized date constant in the where clause. Also, notice that since we have denormalized orders, order line and orders are implicitly joined, as order line is nested inside of orders, so the joined predicates can be removed. py-tpcc is a publicly available benchmarking package for TPC-C. We extended this framework for CH2. As described earlier, we added a configurable run date parameter to seed the data with a date range of 7 years, similar to TPC-H. We added the supplier, nation, and region collections that are not present in TPC-C, and added support for the nested orders collection. We also extended the py-tpcc driver to support analytics clients to run the analytical queries, as the py-tpcc framework only supports one kind of client for running TPCC transactions. To illustrate the utility of CH2, we tested the HOAP capabilities of Couchbase Server 7.0, a scalable document database system. Architecturally, the system is organized as a set of services and that are deployed and managed as a whole on a Couchbase Server cluster. The query service for running OLTP style queries and the analytics service for running OLAP style queries. A Couchbase cluster can be dynamically scaled, and the services can be mapped to a set of nodes in a multi-dimensional manner. The figure shows a typical customer configuration cluster with 3 nodes for the data service, 2 shared by the index and full text service, 1 for the query service, and 2 for the analytics service. A key aspect of Couchbase Server's architecture is how data changes are communicated across services. An internal database change protocol, or DCP, notifies all services of changes to documents managed by the data service. And the corresponding changes are made by each service to keep the data up to date. DCP feeds the data service events to all the other services. For example, Analytics service keeps shadow data sets for each specified collection from the data service, and these shadow data sets are updated when DCP notifications are received about changes to the underlying data. For query processing, the query service orchestrates the data service and the index service in an RPC-like fashion to execute OLTP-like queries fast. The analytics service does its OLAP query processing in a fully parallel manner on its own near real-time shadow copies of the data. Now, we ran CH2's mixed workload on 7 different Couchbase Server configurations with different numbers of query service and analytics service nodes. So we ran the mixed workload consisting of transactional workload and the OLAP workload. The picture illustrates a cluster with 4 query index data nodes and 4 analytics nodes. And the other configurations are 8Q plus 4A, or 8 query nodes plus 4 analytics nodes, 4Q plus 8A, 8Q plus 8A, and 8Q plus 2A. We also ran 2 configurations with 0 analytics nodes, 8Q plus 0A and 4Q plus 0A. Our goal here is to use CH2 to explore several key characteristics of hopeful platforms for NoSQL. Number 1, to investigate performance isolation between the OLTP and OLAP components of a mixed workload. And number two, the scalability of their architectures to support more operational users or a need to perform faster analytics. The nodes used for the different Couchbase cluster configurations were standard AWS M5D.4x large instances. The cluster nodes had 16 vCPUs, 64 gigabytes of memory, 2 SSDs, and 10 gigabits per second network bandwidth. The data, index, and query nodes used one SSD drive for data and the other for indexes. The analytics nodes used both SSD drives for enhanced query parallelism. The client node is an AWS M5D.24x large instance with 96 vCPUs and 384 gigabytes of memory. This was needed to support the large number of transactional clients and analytics clients running on it. It had 2 SSDs and 25 gigabits per second network bandwidth. The benchmark was run with 1,000 warehouses of data with one replica. This was approximately 112 gigabytes of data per replica, and the indexes were replicated on all data nodes. Now we move on to the results of running CH2 on the different Couchbase cluster configurations. First, we show the NewOrder transactions per minute, or TPM results. The graph on the left shows the NewOrder TPM numbers when running only the transactional workload, varied from 4 to 128 transaction clients, and no analytical queries. We can see that the system delivers textbook performance, first increasing linearly and then reaching a plateau when the system's resources are saturated. The graph on the right shows the NewOrder TPM numbers running a mixed workload with one analytical client running the 22 CH queries concurrently with the transactional clients. A second observation is that if we compare the throughputs in the two graphs with and without analytical clients, they are essentially the same. That is, we see effective performance isolation. Looking more closely, we can see that the throughput delivered by the 8 queue configurations are roughly twice the throughput of the 4 queue configurations. That is, the system delivers linear transactional performance scale-up. This is because there is no central coordinator in Couchbase to bottleneck the transactions. The next set of results show the response times for the NewOrder transactions as the number of transaction clients is increased. The graph on the left again shows the transactions only run. The response times are initially flat and then slowly become linearly proportional to the number of transaction clients once the system becomes saturated. The response times are higher for the 4 queue configurations, red, blue, and black lines at the top, and are nicely cut in half, 0.5 versus 0.25 seconds approximately, when the operational cluster size is double to 8 queue nodes, the pink, yellow, and black lines towards the bottom. That is, the system delivers linear transaction speedup. The graph on the right shows the mixed workload run with one analytical client running concurrently. This again exhibits textbook behavior, and the corresponding response times in the two graphs are essentially pairwise identical, showing again performance isolation very nicely. This graph shows the geometric mean of the 22 queries' average response times for the 5 different cluster configurations versus the number of transactional client threads. There are 2 key takeaways that are evident here. First, we see the flip side of Couchbase Server's operational performance isolation. The analytical workload performance is not affected much at all as the number of transaction clients is increased. the geometric mean remains very consistent. Second, we see the very successful linear query speedup. That is, when the number of nodes given to the analytics service is doubled, the CH2 query execution times are cut in half. For example, for the 2A configuration, the geometric mean is about 88 seconds, is about 42 seconds for the 4A configurations, and about 21 seconds for the 8A configurations. Thus, to have your analytical queries run twice as fast, you can simply double the size of the analytics subcluster. To conclude, we introduced CH2, a new benchmark for evaluating hybrid mixed workload performance of NoSQL database systems. We also presented results from running CH2 on different cluster configurations of Couchbase Server 7.0. This demonstrated the value of CH2 as a very useful benchmark for measuring the mixed workload performance and so-called hopefulness of NoSQL platforms. It showcases the strengths and competitive advantage of Couchbase Server's architecture in the NoSQL world, the scale up and speed up for both operational and analytics workloads, the workload isolation, and the full support for SQL, and showed that HOAP is indeed a reality in the NoSQL world also. This work was published and recently presented at the 13th TPC Technology Conference on Performance Evaluation and Benchmarking. Thank you for your time.